Welcome to MET 200, Manufacturing Processes and Material. This is the lecture 9. This lecture we will be talking about ceramic, glass, graphite, and diamond. It is assumed that metal is the most important material for engineering application, but it's interesting that ceramic material are actually more abundant and widely used. In this lecture, we will cover several other elements related to ceramic, such as graphite, carbon, and diamond. Here is the chapter 7 in this book. We try to cover this chapter as much as possible. We first start with the ceramic material. Ceramic, actually, it's a wide-ranging group of materials, and the ingredient of these materials is it can be clay, feldspar, and some type of this ceramic are whiteware, refractory glasses, or some of the ceramic material. We have abrasive and cements. For the feldspar, it's a group of rock forming tectosilicate mineral like this one. And the clay actually contains silicon, aluminum. It also includes the potassium compound, magnesium compound, and calcium compound. In the sand, here, it can contain silica, feldspar, aluminum, potassium silicate. Here in this slide, we see the structure of ceramic material. Ceramics are compound of metallic and non-metallic elements. And the term ceramic, it comes from a Greek word, which is keramis, and it means potter clay. And the word keramikos means clay products. And the earliest use of ceramic was pottery and brick. And ceramic has been used for many years in the spark plug, because it's a good electrical insulator, as well as it has high temperature strengths. This picture shows the structure of ceramic crystal. It's complex in terms of the structure. The type of bond we have in this structure is covalent and ionic, and it is much stronger than a metallic bond. Because of this bond, the properties such as hardness and thermal and electrical resistance are significantly higher than those in the metal materials. And the glasses also considered in ceramic material, but they are distinguished because of their non-crystalline structure. The ceramic can be defined as an inorganic compound, which consists of, as I said before, a metal. It can be semi-metal, as well as one non-metal. Some of the important examples are here for you. Silica, another name for silica is silicon oxide, SiO2, and this is the main ingredient in most glass products. Another example of ceramic is alumina or aluminum oxide, Al2O3. It has a lot of application in abrasive as well as artificial bones. And more complex compound of ceramic can be hydrous aluminum silica, which is this one. And this is the main ingredient in most clay products. We have three different category of ceramic. One is called traditional ceramic, where we have clay products such as whiteware pottery, the brick, some abrasive material, abrasive wheels and cement. These are called traditional ceramic. And then we have new ceramic, or also industrial ceramic, and it's mostly used as based on oxide and carbides, and they have a better mechanical and physical property comparing with the traditional ceramics. And then we have glasses. The glasses are, as I said before, it's distinguished from the ceramic because of their structure. They have a non-crystal structure. The first category, as I mentioned in the previous slide, is traditional ceramic. And the traditional ceramic are based on the mineral silicate, which is silica, one example, as well as other mineral oxide that can be found in the nature. The primary products of traditional ceramic is fired clay, one example pottery, as well as tableware, brick, and the tile. Also, we have natural abrasive in the traditional ceramic, which is aluminum. And the traditional ceramic has a long history. It can be back to thousands of years ago. The last point, the last fact about this ceramic is that sometimes we include glass in the traditional ceramic, and the glass is a silicate ceramic material. In the ceramic material, we have an interesting mechanical property. For example, here, this is aluminum oxide. It shows the transverse rupture, the rupture in strengths, as well as the rupture strengths in the compressive. So the strength in tension is one order of the magnitude lower than compressive strength. This is mostly because of the slip. We have the type of bonding in ceramic, and it is more rigid and does not allow a slip under a stress. We have a structure like this. This is the metal. When we apply external force, the crystal lattice will glide along each other. They become like this. So that they change their crystal arrangement, but we do not see this type of changing in the crystal direction when we are working with a ceramic material. So the inability to sleep makes it more difficult for ceramic to absorb stress. So when we apply this type of loading external force, because we won't be able to see this deformation, suddenly we will have a rupture when the part is in a tensile type of load. Let's look at the physical property of ceramics. The density of ceramic. First, the ceramic are lighter than metals, but if we compare them with the polymer, they are heavier. and they have a high melting point uh, once we compare it with metal. And sometimes they decompose rather than melt, and they have a lower thermal and electrical conductivity comparing with the metals, but the range of value are greater. Sometimes ceramics are insulator, but some of the ceramic can be used as a conductor. This is interesting. So they can be used as a insulator as well as conductor, and they have less lower thermal expansion coefficient comparing with the metal, but the effect of thermal expansion in the ceramic are more damaging because of their brittleness. So they are very brittle. Even a small deformation in the ceramic can cause rupture in the inside the ceramic material. And then the last point is some of the ceramic are translucent. The window glass is one of them, which is based on silica. This table compares the property of metal and ceramic. First is shows the crystal structure. In metal we have a crystal structure, which is the same thing in the ceramic, but in terms of electron, we have a large number of free electrons in metal, but in the ceramic, because of the type of bond, we have captive electron. The type of bond in the metal is a metallic. In the ceramic, it's an ionic and covalent bond. And conductivity, electrical conductivity in metal is good. It's well known. And the ceramic has a poor conductivity if we compare it with the metal. And the ceramic are transparent, but in the metal it's opaque, and we have uniform atom sizes, but here atom sizes are different. It can be large, but some of them can be small. And then we have poor tensile strengths. Here we have high tensile strengths. High shear strength is another property of ceramic, but in the metal we have low shear strength. In ceramic, they are brittle. They are not ductile material, but in metal they are well known for their ductility. We don't have a plastic flow in ceramic, but we have a good plastic flow when the material is in tension. We have a good impact strength in the metals, but the impact strength in the ceramic is very low because they are ceramics are brittle again, and they have a high weight. They are a dense material. They are heavy, but in ceramic, if we compare it with metal, they have a lower weight, lower density. The hardness of the metals are lower than the ceramics. Ceramics are very hard material, and they have high density and in the metal, but in the ceramic we have low density, as we mentioned here. Because of the low density, the weight is going to be lower than the metal. Let's look at the ceramic products. One of them is clay construction product, for example, brick and clay pipe and building tile. And also we have refractory ceramic. The refractory ceramic are capable of high temperature application, for example, furnace wall, crucible, and mold. And also the cement is another ceramic product. Cement, the material we use in concrete and we use it in construction and roads. The whiteware product, which is called fine china, or propylene, and they are ceramic material. The next ceramic products are whiteware, crockery, floor, white tiles are some of them, electrical, propylene, and decorative ceramic, um, such as those shown in this picture. Actually, ceramic has a lot of application in electrical transmission component, also in the computer industry. You can make a wafer. Wafer is a circular, disc made of, ceramic material, and then in the semiconductor industry, then they divide, they cut this, wafer to a smaller piece. Then this smaller piece, this, for example, the rectangle, is going to be substrate, and other component or computer component is going to be um, mounted onto this part. The ceramic has also application in nuclear fuel based on the uranium oxide. We use it in the artificial teeth and bones. We use this ceramic in the thermal insulating wool, reinforced plastic, fiberglass. Also, we use the ceramic in aluminum oxide as abrasive material, silicon carbide in grinding wheel. Also, we use ceramic products in the cutting tool material, such as tungsten carbide and cubic boron nitride. It is also well known that we use cement um, to produce concrete roads and bridge and building. So the cement is another metal type of ceramic material. This table shows the general characteristic and principal use of ceramic. We have three type: oxide ceramic, we have carbide, and then we have nitride. And each one has its own specific characteristic and use. For example, oxide ceramic, this category has a high hardness and moderate strength, and they have a high toughness. The thermal expansion coefficient is close to cast iron, and it's suitable for high temperature application, such as furnace, jet engine component. And the carbide has a good hardness and strength and wear resistance. They can be used as a die and cutting tool. Also, they have a high temperature strength and wear resistance. They are used as a heat engine as well as a abrasive in grinding wheel. In the nitride, which is the second hardest substance known after diamond, are used as abrasive and cutting tool. Their color are gold. They can be used as a coating because of their low frictional characteristics. Also, this material can be used as a cutting tool, as well as feed the tubes. There are other material in this table. We want to pick some of them, but you can read this information later. We have graphite and diamond in the ceramic material. The diamond is hardest substance that we know. It's available in single crystal and polycrystal form, and they are used as a cutting tool and abrasive in the die and for drawing fine wire. Graphite is a crystal form of carbon, and it has a high electrical and thermal conductivity. It can be used as a good thermal shock. And we have carbon nanotube, which is a unique crystalline form of graphite. It has a good thermal conductivity and electrical conductivity. And the last one is a nanophase ceramic, which is stronger and easier to fabricate and machine compared with the conventional ceramic. It's used in the automotive and aerospace application. Let's look at the glass. Glass is an amorphous ceramic material. Actually, it's a ceramic material, and we can produce glass when we cool the ceramic material so quick. So then we won't allow to form crystal structure. If you cool it slowly, then it will form a crystal structure. But if you cool it rapidly, then it doesn't have time to form a crystal structure. Then it will form amorphous structure, and it will consist of disorder and a linked chain of silicon and oxygen atom, as you see in this structure. And this is the main reason for its transparency, as the crystal structure, crystal boundaries scatter the light, and it causes reflection. And the glass can be tempered to increase the toughness and the resistance to cracking. One of the very well-known ceramic glass material is pure silica, is SiO2. In the glass, we have a lot of SiO2 or silica. Why is that? The main reason is that it's a good glass former. We have other material, but normally other ceramic are not a good glass former. So when we cool it down, even quick, they tend to crystallize during solidification. But Si2 silica or SiO2 is a good glass former. We have other material in the glass. For example, sodium oxide, calcium oxide, aluminum oxide are some of them. We have different type of glasses available in the market. One is a window glass. The other one is a container, jars, bottles. They have different composition because their applications. So they have to have different characteristics. And light bulbs. We have beaker in the laboratory. Glassware. Glass fiber that are using insulation and fiber optics, and we have optical glasses, and their properties are summarized here. For example, what is the density of the lime glass, how its strength, electrical resistivity, heat treatability, as well as the cost are summarized in this table. I have a video that shows how the glass is made, but I cannot play here in this presentation. If I do it, then with the YouTube, because the video was in the YouTube, then due to the copyright, YouTube will block my presentation because it has some part of the video that was already in the YouTube. So I don't want to play here. I will post the link in the Blackboard, so if you are interested, you can see the video and get some idea how the glass is going to be made. But this is the schematic of the glass production. The composition is going to be made, and then it's going to be heated up to a certain temperature. It's called, GOP. We have a molten state of the matter. Then it will be settled in the mold, and then the plunger, it has a certain, the desired shape. It's going to descend after some time. When it's pressed, the the molten, glass or the GOP will pick up the shape of the plunger. This is the finished product. Let's look at the properties of glass. Glass are similar to ceramic generally, and they have they are brittle material. The modulus of elasticity, or Young modulus, is between 55 and 90 gigapascal. You remember the Young modulus of the metal steel, the Young modulus is about 200 gigapascal, right? GPa. And for aluminum, it is between 70 and 80. And the Poisson ratio for this glass is between 0.16 and 0.28. If we consider this one, it's very low compared to Poisson ratio of steel, which is 0.3. And glasses are characteristic by their low thermal conductivity and high electrical resistivity. And thermal expansion coefficient, remember that thermal expansion coefficient of glasses is very low. Sometimes it is 0. And they are very resistant to chemical attack, and they are used in the chemical laboratory for carrying acids, and they have a good resistance also against the corrosion. The next material is called glass ceramic. Glass ceramic is a type of ceramic material that is produced by conversion of a glass into polycrystalline structure through heat treatment. The proportion of crystal phase ranges between 90 to 98%, and the grain size is smaller than the conventional ceramic. And we have the actually glass ceramic are opaque. They are not clear when we compare it with the glass material, which are very. Some of the advantages of glass ceramics are stated here. They have a good efficiency of processing in the glassy state, so it can be processed easier. They have a close dimension control over the final shape. They have a good mechanical and physical property. They have a higher strength, stronger than glass, and they have a high resistance to thermal shock. The next material is graphite. Graphite is a form of carbon with high content of crystalline carbon in the form of layer. So remember, this graphite, we have layers, and in the layers we have a different type of bond. If this is two layers, we have carbon in this layer, and the carbon have in here, all of them, they have one type of bond, which is a covalent and a strong. But when we compare the bond between these two layers, the type of bond is van der Waals, and it is weak. And This structure, the layer structure makes the graphite property anisotropic. When it is powder, it's a lubricant, and its frictional property is going to be low. Remember, when it is exposed to air and moisture, right? When it is exposed to air and moisture, it has a low frictional property. But if it is in vacuum, graphite is going to be very abrasive, and it will be poor lubricant. And also, if you have amorphous graphite known as lamb's black soot, which is used as a pigment, for coloring. And graphite has a high electrical and thermal conductivity and good resistance to thermal shock and high temperature. Next material is diamond. In the diamond, we have carbon with cubic as a crystalline structure, and the covalent bond is the type of bonding we have in this material. Remember, the graphite had only covalent bond in the layer. Between the layer, we had a van der Waals bond. So because we have a covalent bond in the diamond, it's a very hard material. It's known as the hardest material on the earth, and the problem with this diamond is that it's brittle, and it began to decompose in air at around 700 degrees Celsius. But if you keep the diamond in non-oxidizing environment, it can resist the decomposing. It has a lot of applications. Some of them are, for example, cutting tool, grinding wheel. And recently, in 1955, they were able to make the diamond synthetically. And the way they produced diamond was that they subject the graphite. This graphite was the raw material. They subjected the graphite to hydrostatic pressure, 14 gigapascal, at the temperature of 3000 degrees Celsius. In that the condition, you can produce diamond. Diamond has a lot of application because of its favorable characteristics. Some of them are a cutting tool, or another, one application is using diamond for the dye to make wire. So you see the wires become smaller and smaller as it goes through these different dyes. So the smallest one is 0.06 millimeter in diameter, so it can make wire with that small diameter. It also has application in dressing of a grinding wheel, as well as coating for the cutting tool. If you have any question about this lecture, please contact me.